Hello, this is Dr. Hassan Abdullah with the course Deep Reinforcement Learning, and we are at topic number 6, and that topic is optimization techniques. The topic is further divided into subtopics, so this is lecture number 6C. So it has the concepts which are of kind of moderate difficulty. And this video lecture, is developed using the supplemental website easymcq.com/goget, which is a personalized learning management system. So we have adopted the approach of content delivery, and this is not like the conventional approach, which has been being used using slides, and it has numerous advantages, and some of those advantages are written in front of you in the slide. So please take a look at it, and you will know the benefits. And this learning management system, which I mentioned, the address is given in the green color URL, and the usage of this personalized learning management system is explained using 6 videos, and the location of those videos is given in blue color. So what are those advantages? It provides very powerful full text and basic text search, which are not there in leading LMS, and it also provides the end user with having any vision limitations to customize the interface. And furthermore, all the content is kind of available in a hierarchy in a drop down menus, which supports working and learning on a smart device with limited screen. Then it tracks your progress, so you know what you have done, what you need to do. And then of course there are online exams with online grading, and averaging the results and letting you know what is your level of understanding. So we have used the approach of question and answer, which is more engaging, which is more proactive, and which promotes thinking. And of course, we have also used the traditional learning approach, where details are provided. So this is a blended learning mechanism, which is the best of both worlds. And these are the topics which are covered. And we are at topic number 6, which is the optimization techniques. And the details of this topic is in front of you. So we have these blocks of color which identify which concepts Q&A are covered in which topic. Say for example, lecture 6A shown in yellow covers the first 3 Q&A or the concept. Similarly, in green color is the next 3 Q&A, which is 6B, and so on. So without further ado, we move on to the actual course and start from there. So we are at section 6C. So what are the issues of cliff and exploding gradients in deep learning? So what are, as a matter of fact, cliffs? Cliffs basically are steep, abrupt changes in the loss surface, and it causes problem because it increases the gradient or the magnitude of the gradient. So what's going to happen is that when an optimizer encounters a cliff, it may take large steps. So when those large steps are taken, they drastically alter the model parameter. So what is the consequence at the result? That it often disrupts learning, causing instability, which, as a matter of fact, makes it harder to approach an optimal solution. As a matter of fact, large jumps can just skip the optimal or the global minima, even in fairly simple loss surfaces, which we have discussed already. So cliffs are particularly dangerous when there is a high learning rate or if the parameters are not properly initialized. And what are exploding gradients? This basically refers to the phenomena when gradients grow exponentially during back propagation. And this is particularly true for deep networks. So these excessively large gradients cause massive updates to the weights, as a result, which destabilizes the entire training process. So if it is not addressed properly, exploding gradients can make the model untrainable. So you can see over here there is a drop, so to say, okay, and the slope of this drop is almost infinite because it's almost vertical. So what we'll be covering is the larger or the large parameter updates for cliffs. Okay, and oscillations we discussed before, that because of the large jumps, okay, the optimizer moves across the volume, okay, or the surface to be more precise, and it kind of misses the global optimum. So let's go into some more detail. All right, so when large parameters updates takes place when large parameter updates take place, okay, it happens when the gradients are steep and often near the cliffs, as the case is over here. So these updates can cause the model to overshoot the optimal region because the step is very large, and leading to erratic loss values and instability because it just keeps on jumping and trying to get to the local minima, let alone the global minimum. Now, this behavior can prevent the model from settling into a useful minimum, not the global minimum, but a useful minimum, and often results in poor convergence or divergence during training. That we have seen before also. Oscillations and slow convergence. When the parameter updates are too aggressive or misaligned, the optimizer may bounce back and forth across the loss surface, which creates oscillation because the optimizer is trying to converge to the local minima. But because of these large aggressive parameter updates, it misses it, and that results into oscillations. And that is not that is just waste of computing resources and energy. So this back and forth behavior slows down learning. Why? Because the model fails to make consistent progress towards the minimum. It's just oscillating. So as a result, the learning is reduced, and of course, or using momentum can help alleviate this issue. Okay. Now the difficulty in convergence. Now convergence becomes difficult when the model fails to minimize the loss over time. So what's the result? Repeated large updates or oscillations caused by the cliffs instead of gradually approaching an optimal solution. The model kind of fluctuates, okay, and unable to learn any meaningful representations from the data because of the cliffs. All right. So the details are at the. I'll show you details. So for exploding gradients, the training is unstable. This is a direct consequence of the exploding gradients. So what happens is that the model's loss becomes highly erratic, again fluctuating or increasing uncontrollably. So the training process fails to follow a predictable pattern. So the progress cannot be judged or determined if the model is improving or not. Numerical instability. So when the gradients become too large, they can cause arithmetic overflows, divide by zero error, so or NA and not a number, or infinites in the weight value. This is called as numerical instability. Now, once this occurs, the model's parameters can no longer be updated correctly, and that effectively corrupts the learning process. And finally, the difficulty in learning. Now, these exploding gradients make it very difficult for the model to learn because of the instability and effective weight adjustment. The training might start well, but the training stalls or crashes due to massive parameter shifts or invalid numerical values. So we have the techniques like gradient clipping or better initialization, which are required to restore the learning ability. So if you are interested in the details of what I have covered, these are the details here, and here are the references. Okay, so this is the next concept. So now let's look at stochastic gradient descent. And what is the significance of stochastic gradient descent? It is a widely used optimization algorithm in deep learning and machine learning. So what happens is it functions by updating model parameters based on the gradient of a loss function, and that is calculated using a random subset, a mini batch of the training data. So what is the advantage? That instead of being very kind of linear or deterministic, it adds some randomness into the training process, which makes it very efficient, especially for large data sets. So SGD, or stochastic gradient descent, follows an iterative process of sampling the data, calculating the gradients, and updating the parameters. So what allows the model to gradually converge towards the minimum loss. So basically, this basically shows a valley or the minimum value. So using gradient descent, the control works this way, all right, which is shown in the red color, and the stochastic gradient descent is shown here. So we'll discuss how it works and what is the significance of stochastic gradient descent. Okay, so this is the points we'll be discussing. So the significance of stochastic gradient descent lies in its practical advantage, because it doesn't require processing the entire data set at once. So of course that results in reduction in processing time, and the random updates help the optimizer to converge faster, and it helps to escape the local minima, unlike the batch gradient descent. Furthermore, the noise or the randomness introduced by the stochastic updates can have a regularizing effect. What is that? It prevents overfitting. And because of its simplicity and adaptability, it is scalable across various models and hardware setups, which could be small networks to large scale deep learning systems. So it kind of strikes a balance. So how does stochastic gradient descent works? Okay, it involves random sampling. So what is random sampling? It selects a random data point or a small batch from the training data set during each iteration. So of course that reduces the computational overhead compared to using the full data set, which can be several times more than the small batch. Now this introduces noise in the training process, but this randomness allows for faster and more flexible updates, which makes the optimizer more agile and less prone to getting stuck or landing into oscillation. Okay, and then are the gradient calculations. Now for each sampled batch, sampling is a subject in itself. So SGD computes the gradient of the loss function with respect to the model parameters. So these gradients represent model parameters, and these gradients then indicate the direction in which the loss increases. So when that direction is identified, this allows the model to adjust the parameters in the opposite direction to minimize the loss, right? So this is the key step which is used for learning from data. What is meant by parameter update? Now that the gradient that has been computed, SGD updates the model's parameters by moving in the direction opposite to the gradient. And then this is not kind of a free movement, but there's a learning rate, and it is scaled by the learning rate. Now this update helps the model to improve the predictions over time. So the size of the step is crucial for balancing speed and stability. Now if the size is very small, it will take a long time, but it will be more precise, but it will cost more. If the size of the step is large, okay, it can result into oscillations, and it can easily miss the global minima, even the local minimas also. All right. And this is an iterative process. So the process of or the cycle of sampling, then the gradient computation and parameter updates is done over many iterations, which are called as epochs. Now, what happens that in each iteration or epoch, okay, the model parameters are gradually refined by the data. Although this is noisy because of sampling, but this iterative nature allows SGD to adapt continuously and approach an optimal solution with sufficient training. That is possible. So, what is the significance of stochastic gradient descent, right? So, it will help if you look at the picture here also. So, it is its efficiency with large data sets. Large data sets. So, since SGD can work with mini batches, it can handle large data sets, which cannot fit entirely into memory. So, what is the advantage? It makes the training feasible with the resources which are available, and that training is also efficient, even on modest hardware, because sampling is done. So, because of that sampling, the computational load per iteration is reduced. So, as a consequence, within the given processing time, frequent updates can take place, and there is a quick feedback during the learning process. Okay, then is the faster convergence. What is meant by faster convergence? Now, since the updates are frequent and stochastic in nature, uh, and it is dynamic also, so SGD converges faster as compared to the batch gradient descent, especially during the early stages of training. Now, it is true that individual steps may be noisy, but the overall trajectory moves towards the optimality because of the repeated iterations and fine tuning. So that makes it ideal for time sensitive applications or resource limited environments with modest hardware. So how can it escape from the local minima? Okay, how can it escape from the local minima? Because of the inherent randomness. Okay, so shallow and local minima or saddle points in non-convex regions are a lesser issue. So what it does, it improves the SGD ability to find better global or near global solutions. So this is the strength as compared to deterministic methods. It doesn't always follows the smooth path. As a matter of fact, the deterministic methods will more likely to follow the same path. So not always follows a smooth path, SGD, and that can be an advantage in deep learning. Now, what is the effect of regularization? So the noise which is kind of introduced by SGD is not explicit but implicit regularization, and it prevents the model from not only from prevents the model from overfitting to the training data. So this improves obviously this improves generalization for the unseen data. So the randomness forces the model to learn more robust patterns instead of memorizing specific data points. So and because of this, the regularization improves. So there is less overfitting. And finally, the scalability. Now, SGD is easily scalable across different computing environments. That could be distributed systems and GPUs. So this mini batch nature allows parallelization also and distributed training also. So as a consequence, it is like obviously suitable for massive data sets and deep neural networks. And this is the reason why SGD uh, has widespread adoption in modern AI frameworks. All right. So I've not given a lot of details, just set you in the right path. So these are all the details, all right? So I would strongly suggest you to read those details, and you are interested, these are the references for you for further reading. So we now move on to the next concept. So now we look at the significance of the learning rate in deep learning. So what is learning rate? Learning rate is a critical hyperparameter in the training of deep learning models, and what it determines is the step size at each iteration. We covered this before also, and this happens while moving towards the minimum of the loss function. Now, if I could put it more simply, it controls how much to change in the model's parameters with reference to the estimated error. And when does it happen? Every time when the model weights are updated. So what it does, it of course controls the speed of convergence. And because if the step size is large, it will behave differently. If the step size is small, it will behave differently. And it affects the stability of the training. It can result in oscillations also if not properly used. And this is the strength, dynamic learning rate. It should not be static. And whatever happens is it happens with reference to the batch size. So these are the details of these bullets which we will be covering. And as you can see that if the for a very high learning rate, okay, the loss can be very high also, but the epochs are less. And if this is very high learning rate, and when we have low learning rate, okay, the loss is reduced, of course, but the epochs are increased, and this is not very gradual. See, low learning rate versus good learning rate, this is very gradual in green color. So what does the what it does is as follows. It controls the speed of convergence. So basically the learning rate determines how large each update step is going to be during the training. Obviously a higher rate can speed up convergence, but it can result in oscillations, and it can result in the risk of overshooting the minima because the large step. Obviously a lower rate slows the learning, but since it's small rate, so allows for finer adjustments. And of course in either cases proper tuning is required, is essential for efficient and accurate training. Then the effects, and this learning rate affects the stability of training. Now if the learning rate is not chosen properly, it can destabilize the training. If too high, of course there won't be any it can cause the loss to divergence. If too low, okay, it can stall, and when it gets stalled, it can get stuck in suboptimal regions. So what we are looking at is a stable training, or the stable training rate, okay, a well balanced learning rate which can ensure smooth and reliable progress. All right. So dynamic learning rate. Now why it's called dynamic, because the learning rate adjusts during the training. So it may either decrease over time or it may increase over time, but it's going to change, and it's going to change based upon the performance. So there are techniques like learning rate schedules or adaptive optimizers like ADAM, which improve convergence, and they even avoid local minimum, and that enhances generalization. How? By tailoring the rate to the model's learning phase. All right. And finally, the relationship with the batch size. Now, the learning rate usually interacts with the batch size. Now, large batches produce more stable gradient estimates, which can support higher learning rates. And the converse is true for smaller batches. Now, if we are able to tune them together, both of them. So that allows, and it is critical for achieving optimal training performance. So this is the diagram which we discussed, and these are the details, and here are the references for further reading.